Okay, ladies and gentlemen, today we are on to the third and final rock type, which is going to be metamorphic rocks. Now, we've already gone over what a rock is, and we've taken a look at igneous rocks, we've taken a look at sedimentary rocks, so now the third and final type is the metamorphic rocks. Now, what we have discovered so far is that sedimentary rocks are going to form in a certain way. Igneous rocks are going to form in a certain way. Well, metamorphic rocks are also going to form in a certain way, and that's what makes all of the different rocks unique, meaning how they form. Sedimentary rocks, you have, and again, I'm going to just jump to the reference tables. Sedimentary rocks, compaction and cementation, deposition and burial of sediments, and weathering and erosion. All of that makes a sedimentary rock. Igneous rocks, you have to have melting into magma or lava. You solidify to become igneous. Metamorphic rocks, all right, comes down to what it means. What metamorphism means. Metamorphism means to change. So, as we can see, we're going to start off as one thing. And for those of you who have never seen this before, it's actually one of the coolest things that you can see in science. Right? This is a cocoon, and what comes out of a cocoon? A beautiful butterfly. So rocks can do the same thing. Rocks can change, right? For example, we have shale. Who remembers what type of rock shale is? Shale is going to be a sedimentary rock. But over time, right, shale can be changed or morphed into something we call gneiss. Notice they are two completely different looking rocks because it was changed. So how do we create a metamorphic rock? Well, we're going to take a look at the reference tables, and if you're a metamorphic rock, in order to become it, you have to be something else before, right? Now, let's just kind of work backwards. So metamorphic rocks, heat and or pressure, which has metamorphism, meaning to change, will become a metamorphic rock. If you started as a sedimentary rock, added heat and or pressure, and now we're not talking like just a little bit of heat and a little bit of pressure, you have to add a lot of heat or pressure. Picture deep underground, an earthquake, the tectonic plates squeezing all that rocks together. That will create heat and pressure and morph or change a rock. So, sedimentary rocks, heat and pressure to become metamorphic. Igneous rocks, heat and or pressure, metamorphism, metamorphic. And notice, whoosh, swoop right around here, heat and or pressure, metamorphism becomes a metamorphic rock. So, sedimentary, igneous, and metamorphic rocks can become metamorphic rocks. All right? So, you need those two things, heat and or pressure. So when we're looking at it, right, you can have essentially two different types of metamorphism. You can have what's called contact metamorphism, right, or you can have what is known as regional metamorphism. We're going to talk about them in a little bit more in depth, all right, where you have the plates moving. But this area down here, right, where it says magma chamber, and these rocks that are forming in there, what must those be? Well, since we have magma, we have to be igneous. Contact metamorphism, right, will only be on this border, right, not where the rock melts. Melting creates igneous. Heat and pressure create metamorphic, okay? Now, why metamorphic rocks tend to be the most challenging to identify is because they're going to take on the characteristics of what they were before. So the new metamorphic rock is going to be similar to its parent rock, right? Just like if you take a look at yourselves, right, you have some similarities to your parents. Are you exactly like your mother? Are you exactly like your father? No, but you have some of their characteristics. So they're going to tend to be more dense because of that heat and pressure, that squeezing, and less porous. Meaning, if you have an igneous rock that had vesicles or holes in it, add heat and pressure to it, that rock is going to be squished. No more holes, no more vesicles. Okay? So, now, when we identify a metamorphic rock, we're going to, and again, I'm going to jump to the reference tables, right? And your metamorphic rock chart is now on page 7, so we're on the bottom of page 7. The first thing you want to look at is your texture, right? So First texture we have, and I apologize it doesn't fit, is going to be mineral alignment. So mineral alignment is right here, part of a foliated texture. So what does mineral alignment mean? This is where the minerals begin to actually line up. So when you add heat to a rock, it's going to become soft. Think almost like jello or pudding. Right? Pudding is not really a liquid, it's not a solid. It's kind of that semi-solid in between, right? And things inside can move around. So minerals are going to be able to line up to a 90-degree angle in the direction of pressure. So what does that look like? Right? This is a metamorphic rock. See how all of these minerals on the sides here, right, are lined up kind of like this, and on this side they're lined up like this, and these are flat. That's because the pressure, indicated by this red line, pushed down and pushed up, squeezing it together. Picture taking a piece of paper. If you took a piece of paper, or a whole bunch of pieces of paper, and randomly threw them on your desk, and then put your hands on the side of the desk and pushed in towards the middle, every piece of paper that you hit would kind of bend, fold, and squeeze in between your hands and lining up in the same direction. That's what we call mineral alignment. Okay, now there is a more extreme type of alignment or foliation, which is known as banding. Okay, now with banding, this is where all of the minerals, right, really line up and create bands or wavy lines in the rock. Banding can be confused with sedimentary layers. The biggest difference is you'll actually see the minerals. These will be shiny and sparkly. I always like to describe it as tiger stripes. Okay, so banding is a type of foliation where minerals have lined up to make clearly visible bands. All right, please do not confuse these with the layers in sedimentary rocks. All right, if the rock has visible grains and particles, it is not metamorphic, meaning if you see essentially the pages in the side of a book layered perfectly flat on top of another, that is sedimentary layers. Metamorphic banding will usually be curved because we have a lot of heat and pressure. All right, sedimentary layers are going to be flat. So again, picture the stripes on a tiger, right, for banding. All right, banding is tiger stripes. Okay, if you picture the stripes on a tiger, you can see those stripes on all sides of the tiger, not just the top, not just the bottom. All right, all sides. Can you see the pages in a book from all sides? No, you can only see it around the outer edges, not the top and the bottom. Okay, so tiger stripes is banding. All right, and banding creates a very nice rock. We can see right there. All right, so let's take a look at this. So we have banding, we have alignment, or we have sedimentary layers. Now, when the first one popped up already. Now, when we look at this, does this look like we have perfectly flat layers going across? No, that's why it's mineral alignment, right? You see kind of lines that start, right, and stop, and I'm just going to kind of highlight them a little bit here, all right? This is your mineral alignment. Let's jump over to this side. Notice we have these very clear, almost perfectly flat lines going right across, and I can't draw a straight line, I apologize, right, going straight across. That is going to be our sedimentary layers, right? Then here on the bottom, we could see very clear, right, arrangement of light and dark minerals, but they are combined into bands. Doesn't this kind of look like the stripes on a white Bengal tiger? Right? Again, tiger stripes, alignment, and sedimentary layers. Okay, now when we think of this, all right, we have again alignment and we have banding. Now, when we think of these, grain size, this part here is not really important. Right, so we're going to cross that off. Not super important because it's not really going to help us that much. Make sure you can read it, but it's not really going to help us. Right? And we come to the composition. These are the minerals that are in the rock. So when we think of this, if this rock on top here is only made up of one mineral, it's going to have essentially a uniform color, meaning it's going to look like one thing. these next ones can get a little bit more confusing because they have many minerals in it, and I will talk about those in a few moments. All right, so there are essentially two ways that metamorphic rocks form. The first one is called regional metamorphism. All right, regional meaning big, right, area. Okay, big area. So regional metamorphism, you have to picture kind of like on the side of a volcano or in a mountain range, right? You have a really big area. Okay, so what happens, right? You have rocks that are put under intense heat and pressure. The rocks are forced upwards, usually from the collision of the tectonic plates. This adds, again, there's that heat and pressure, it comes back, tremendous amounts of this heat and pressure, and it relates to a high degree of metamorphism, meaning a great amount of change. So where do we see this? Here is a mountain, right? We could tell pressure is coming in this way, right? Squeezing this way, right? And squeezing this way, because this is starting to kind of pop up, right? Squeeze like paper, right? So regional metamorphism, right? We can see it on top here. And notice it says heat and pressure increases. So down here you have high pressure, right? And up here you have low pressure. So this is going to be very changed. This is going to be a little changed. So how does this work? Let's take a look at the comments. Low-grade metamorphism of shale. So shale is what type of rock? It's sedimentary. So shale is the parent rock. If you add a little bit of heat and pressure to shale, it's going to become the metamorphic rock slate. Now, as we work our way down, all right, we're going to add heat and pressure. So if you add heat and pressure to slate, slate is going to become phyllite. All right. Now, the way that we identify phyllite is it's going to have shiny, right, mica crystals. Right? Shiny mica crystals in this. So how do we see that? Well, it's going to be a very shiny rock, but now this mineral here, garnet, is in phyllite. Garnet is a very, very, very hard mineral. So this is actually going to have, right, garnet, I apologize, garnet pimples, right, in this rock. All right, garnet pimples. So the rock is going to be very, very shiny from these mica crystals right here, the mica crystals, but then there's going to be these kind of really dark, almost blackish bumps that are going to pop out of the rock because garnet hasn't been essentially reconfigured or metamorphized into another rock. All right, so these garnet pimples, right? If we add a little bit more heat and pressure, phyllite is going to become a piece of schist. All right. So how do we identify schist? Well, schist has platy mica crystals. All right. Now, how do I like to describe platy mica crystals? Easiest way to identify this is think of a fish. All right. Those scales, all right, on the side of a fish look like little plates, all right, or armor. Right? So the schist is going to have fish scales. It's going to look like platy mica crystal. So the rock is going to have fish scales on it. You're going to see the alignment of the minerals on the sides of the rock. And then if you look at the top of the bottom, because everything is going to be squished and flattened out, we're going to get these nice fish scales. Right? Then finally, all right, we take this piece of schist and add more heat and pressure to it, and it becomes gneiss. So yes, only in earth science, right? This is an earth science joke, right? Only here in earth science can you take a piece of schist and turn it into something nice. Now, I do not suggest that you try this at home. Please remember, this isn't a metamorphic rock. Please do not go into the toilet and grab the stuff that comes out of your body into the toilet and try and squeeze it really hard. That is not going to make something nice, right? That is going to make your hands full of a brown material that you are not going to be very happy with, all right? So schist is in metamorphic rock, add heat and pressure, and it will become gneiss, all right? And this gneiss is the highest grade of metamorphism, and this is the only one that we see banding, all right? Again, tiger stripes. right? Tiger stripes. And now, the last part of this chart is the map symbol. These are symbols, all right? They're not pictures, meaning this is not what the rock looks like, but it kind of helps a little bit, all right? Here are your pimples in the rock, all right? This does not look like fish scales, sorry, right? But these do look like the wavy bands or what would be tiger stripes. So, okay, here are your regionally metamorphized rocks. So, jumping back to this, right? If we have the sedimentary rock sandstone and you add a little bit of heat and pressure as you get closer to the center here, it can turn into quartzite. We'll talk about that in a little bit. All right, if you take the sedimentary rock dolostone or limestone, right, it can change into marble. How do we identify limestone? Think, what is limestone made of? Calcite. How did we identify calcite? Acid test. Limestone, acid test. Marble, acid test. All right, then siltstone can change into hornfels. Again, we'll talk about that. But now the one we just went over. If you take the sedimentary rock shale, add a little bit of heat and pressure, it's going to become slate. Add a little bit more heat and pressure to slate, you become phyllite. A little bit more heat and pressure to phyllite, you become schist. A little bit more heat and pressure to a piece of schist, and yes, you become gneiss. Now, notice that you are getting closer and closer to the granite mountain core, meaning granite is igneous, so this was lots of heat, lots of pressure from being buried underneath. Right? The second type of metamorphism is known as contact metamorphism. Right? Contact means that you have touching. Right? So this occurs where you have an igneous intrusion. Right? The igneous intrusion, right, is going to force and melt its way through other layers of rock. Now, where that magma touches the other layers, they're going to become hot. They will then change and recrystallize by the intense heat. Notice, just heat, no pressure, no pressure. There is not much pressure applied here, right? So this is a lesser or a lower grade of change. So here is your magma, right? Your contact occurs right on the edge where you'd have that recrystallization, right? You're not actually melting. If you melt, you become igneous, right? So notice all of these are sedimentary. Here is your magma igneous. Your metamorphic is going to be on that boundary between the two. And the way that we usually see that in the form of a regions question would be over here on the right. All right, see these little like caterpillar fingers? All right, that shows you that it's contact metamorphism. And it's going to be your job to understand, right, that this symbol in here is basalt. Basalt is igneous. This symbol over here is granite. Granite is igneous. So those are your igneous intrusions, and this creates that contact metamorphism. So in thinking of that, right, you would be able to then use this picture to figure out and identify what type of metamorphic rock. So here is that chart, and I'm going to jump back to the reference tables where I've been writing. So this is our bottom chart. Non-foliated means that there is no alignment and no banding, so no arrangement. Okay, the way that we identify this, right, is essentially what the mineral is, what the composition is. Again, this is not really going to help us, so we're going to cross out this column. All right, but what does carbon look like? Carbon is a black mineral, right? Black mineral, right? Only formed during regional metamorphism, right? And it is the metamorphism of bituminous coal, which, if you remember back, was a sedimentary rock. Here is your bituminous coal. All right, so if you add heat and pressure to bituminous coal, you're going to become anthracite coal, which is the metamorphic version. Okay, so this is the parent rock. This is what it becomes. All right, now, all right, hornfels is kind of like your get out of jail free card because hornfels can be formed from various rocks, meaning any rock that is formed from contact metamorphism can become hornfels. Hornfels is we're not really sure what it is. That's what various means, right? So if you're not sure and hornfels is an answer choice, and we're talking about contact, this is always a correct answer, right? Now, next. These next ones can be regional or contact. So the mineral quartz, If we have quartz sandstone, right, will become quartzite. So if we take sandstone and metamorphize it, it will become quartzite. So I'm just going to jump back to the notes here, right, and go up. So this rock symbol up here tells us it's sandstone. Here is that igneous intrusion. Here is your contact metamorphism right on that boundary there. So what type of rock can we find here? Right? Since this is sandstone and this is igneous, this is your contact metamorphic rock, so this is going to be quartzite. Right? Quartzite, and I apologize for the writing, right? Quartzite on that border. So sandstone, quartz sandstone, igneous, metamorphic, quartzite. Right? So that's how we figure it out. Right? Next, calcite or dolomite, those are the minerals. We metamorphize it, right? Meaning you can have limestone or dolostone, and if you change it, it will become marble. All right, so we take a look at this, right? See, we have this kind of wavy here, right? That wavy symbol, there is your wavy symbol, so that is marble. Right? And then this is the easiest one to identify when you see it, right? Metaconglomerate. Well, conglomerate was our sedimentary rock. Remember, conglomerate had rounded fragments in it, so picture jelly beans. So metaconglomerate is going to be essentially those jelly beans, or the pebbles may be distorted or stretched, meaning take those jelly beans and smush them. All right, so metaconglomerate, the parent rock is conglomerate. So let's quickly review these. All right, anthracite coal, parent rock, bituminous coal, quartzite, sandstone, marble, dolostone or limestone, metaconglomerate, conglomerate. Those are your parent rocks, or where it came from. And on the top are parent rocks. Gneiss came from schist. Schist came from phyllite. Phyllite came from slate. Slate came from shale. Those are our parent rocks. All right, so that's how that chart works. All right, so let's quickly go through the questions. Describe the texture of marble. So jump to the reference tables. We find marble, right? And the texture of marble, right? Well, look, texture is a non-foliated, meaning that it is going to be, right, unorganized. There's no banding, there's no alignment. Describe the texture of gneiss. Gneiss is up here. Gneiss is foliated, but it is banded. So we're going to go a little bit further, all right, because banding is the true real texture. All right, now, can a rock formed by contact metamorphism show foliation or banding? Jump back. So contact metamorphism, right? Only down here, regional or contact. These can only be non-foliated. So can we have banding? No, no banding. There's not enough pressure. Remember, contact only forms from heat, no pressure. All right, what is the difference between the sedimentary rock conglomerate and the metamorphic rock metaconglomerate? Well, it's the comments, all right? Pebbles may be distorted or stretched. So picture those pebbles smushed. All right, smushed jelly beans. What are the minerals that make up phyllite? So phyllite, you go over to the minerals. So if the bar graph extends into it, that mineral is there. So mica, quartz, feldspar, amphibole, and garnet. No pyroxene, right? Does not get there. Oop, sorry. Right? Shale is a sedimentary rock. If we put it under heat and pressure, metamorphism, what will it become next? You saw it, but here is shale. Shale will become the metamorphic rock, slate. All right, and we follow this through. If slate is a metamorphic rock, add more heat and pressure, you will get slate becomes phyllite. Right? And so this is what slate looks like. This is what phyllite looks like. If we add more heat and pressure, we're just going to follow our way down the chart. Phyllite becomes your piece of schist, foliation and mineral alignment, and this is schist, right? Then if you add the most heat and pressure, you're going to get gneiss, which shows very clear bands. And you can see the tiger stripes in this. All right, and now going through this really quick, do we have regional or contact metamorphism? So slate, here is slate. Slate is regional. Hornfells down here, only by contact. Phyllite up here on top, regional. Quartzite. Here is quartzite. Regional or contact, so it can be both. Gneiss, up top. Very nice looking rock too, right? Is in the regional area. And finally, metaconglomerate. Metaconglomerate, regional or contact, so both. All right, so that concludes the metamorphic rocks and all three of the different rock types. Remember, if you have any questions, right, or anything about metamorphic rocks or the chart in the reference tables, please feel free to reach out. Whether you message me individually or send me a message on Teams, I will gladly answer any questions that you have.